we're looking at what they call stationary point, critical point, turning points. All right? I had copied this diagram from a ebook. Let's see something. Yeah, Calculus and its Application, 10th edition by Bittenberg, Ellenborn, and Sergeant. All right, very good book. Recommend you purchase a copy, copy of the physical printed book. All right. Now here, this is curve of a made-up function. All right. You have various curves of functions. For example, you might have, let me get one or two functions here using GeoGebra. So, an example of graphs that show some functions or the other. So, for example, suppose you have x squared, y equals x squared plus 3x minus 1. So we have the function y equals x squared plus 3x minus 1. Right? That's the function there. Y equals x squared plus 3x minus 1. Now in this case, you have a minimum point here. You have a curve here and a minimum point. It could be another case where, for example, I have y equals x cubed minus 3x minus 1. That's how it looks. And then I put 3x squared raised to the power of 2. And you have another case here where you have two turning points. In this case, you have a minimum and a maximum point. Let me make it thicker. You can see it more clearly. Over here you have a maximum point. Over here you have a minimum point. Right? Now this is called a local maximum point because if you go across, there are points higher than it. So it's only maximum within a small region, within this region. This is also a minimum point, but you call it a local minimum point because if you go to the left straight across and then you have this point here, what you call a minimum point, coincide with here, but you have other points that are lower than it. So it's not the absolute minimum point. It's a local minimum point because there are other points lower than it. This is a local maximum point because you have other points higher than it. If you have another case, suppose I put this back as squared, then in this case what you have is an absolute minimum because it's quadratic and there are no points that are lower than it. And if I do this now, let's say I have negative 5x squared minus 1. This is an absolute maximum because it's quadratic and there are no points that are higher than it. So it's maximum point. Alright? So here, we're looking back at this. F prime x when you differentiate. But before we talk about this, let's look back at our screen over here. You see at C1, you will see a line, horizontal line here. You have it here at C2, C4, C7, C8. Because the gradients at those points are 0. You remember that? The gradients at that point is a 0. So right at this point where you have a relative maximum, the gradient is 0. A relative minimum here, the gradient is 0. Remember, once you're at the top of a hill, you're at a maximum point. So at this maximum point, the gradient is 0. This is at the bottom of a valley, a local minimum point. The gradient here is also 0. Same thing happens here and here. This now, the gradient was increasing. Well, it was high and then decreasing. It goes to 0, but it did not turn negative. It starts increasing again. This is called a point of inflection. Alright? Because it did not turn. It's not a turning point. This is a turning point because the gradient would have turned from maximum, from positive to negative. What I mean by that is this. Let me get a ruler here. The gradient turns from positive to negative. What it means, if I should find the gradient, let's say somewhere on the left of the point, I would do this, right? And then I would draw my line on the ruler. I would draw my line along the ruler. I want a line on the ruler. My gosh. If I line up and draw along the ruler, well, I wanted a straight line. Then, what I have is a line with a positive gradient. That is to the left of that point. Alright? Suppose I find the gradient of a point to the right of that point. I would have to line up the ruler like this. And then I draw my line along the ruler. And that has a negative gradient. You see that? So to the left, there's a positive gradient. To the left, there's a negative gradient. But if I should find the gradient, if I should use a ruler to line up right at the top of the hill, right at C1, then the line that I would have to draw is this. And it has a gradient of 0. So it's a horizontal line, and you know that a horizontal line has a gradient of 0. So what that means, if you find the dy by dx for this function, and then you put the value of x at c1 in it, and you work it out, you're going to get 0. And we'll do 1 or 2 examples later on, right? So that's a turning point. The gradient turns from positive to negative, right? Gradient turns from positive to negative at that point. The gradient will turn from negative to positive at this point, right? Now, what happened at C3? The derivative does not exist. As it says here, f prime x equal f prime c equals 0 at c1, c2, c4, c7, and c8. That is the tangent line to the graph is horizontal for these values. Alright? So you see, at that point of inflection there, if I should put the curve, the ruler right here and draw the line, I will get a horizontal line. Just like what happened at C1, C2, C4, and C7. Alright? Now, f prime x does not exist at C3, C5, and C6. The tangent line is vertical at C3. Now, it's vertical at C3. You see at C3, the curve goes straight up. Right? If I should put the ruler there, it will go straight up. Now you know that at that point, dy by dx would have an infinitely large value, because you have a change in y and no change in x. So to find the gradient of that, you would be finding a change in y, call it delta y, over the change in x, which is 0, and you're trying to divide by 0. So in that case, you have a situation that is undefined. Alright? And then here, there are corners at point C5, right here, at C5, and C6. You have corners there. So, the derivative does not exist at those points. Alright? So there you have that. Now, suppose, for example, you had dy by dx. Let's look back at our GeoGebra graph. And our function that we had before. Let's look back at turning this function into a cubic function. Y equal x cubed plus 2x squared minus 1. There we have our cubic function. Let's zoom in into our function. Get a closer look at it. Alright, so this function, let's show the label for the function so we don't forget. X cubed plus 2x squared minus 1. So the x cubed plus 2x squared minus 1, it kind of looks like this. And you have a negative 1 point, let's say 35. It's approximate. Negative 1.35. And we have a, it looks like it crosses it at x equals 0. And 0 here. So we have our x-axis and our y-axis there. This was our x-axis, and our y-axis is up here, somewhere up there. Alright? We're just trying to replicate the graph, but not perfectly. So you have that point there, it's about 0. About negative 1.35. It should be kind of close. And the function was x cubed plus 2x squared minus 1. So y equals x cubed plus 2x squared minus 1. What is dy by dx? dy by dx in this case would be 2x squared plus 4x. Now if you should try and solve this, let's factorize this now. 2 outside the bracket, 2x outside the bracket. What you'd have inside the bracket is x plus 2. Alright? X plus 2. So, here now. What are the values? By the way, hold on. Let me see something here. Okay, 1.35. X cubed plus 2x squared minus 1. Okay, good. X cubed plus 2x squared minus 1. So yeah, oh, my. I made a mistake here. It's 3x. This should be 3. 3. So it's 3x squared plus 4x. My mistake. We have to make a little change to that. So this amounts to, when you factorize, it would be x outside the bracket. Inside the bracket, you have 3x plus 4. Now, what are the points at which this is equal to 0? Now, here, we have x, 3x plus 4. Right? At what value of x will make this equal to 0? Well, in one case, if we should equate this to 0, then on one value of x will be x equals 0, because 0 times 3x plus 4 is 0. So we get this minimum point. The other minimum point is when 3x plus 4 equal to 0. What would x be? X would be equal to negative 4 over 3, which is negative 1.33. Oh, it was trying 33. Right. But just by eye, I was estimating it. So it was negative 1.33. So you notice what happened? You have the function. I differentiated it. What I get is the gradient function. I have the gradient function. Equate it to 0 and solve. I get two values of x. Now, here, those values of x will be the values of x where the gradient function is 0. That means the gradient of the curve of the function is 0. I get x equals 0 and x equals negative 1.33. Because this is a gradient function, you know. Where will the gradient function be 0? I just equate it to 0 and find the values of x where the gradient is 0. It happened to be here and happened to be here. You see that? So, if you want to find where the gradient of a curve are 0, you're going to find the stationary points. Then differentiate the function to find the gradient function. Where there will be 0, equate it to 0 and solve for x. Those values of x are the values where the gradient will be 0. Alright? If you are asked to find the coordinates of the critical points, then you already have the value of x here. Put that into this, and then you're going to find the y value, negative 1.33 cubed plus 2 times negative 1.33 squared minus 1. So what you're going to get is when x equals negative 1.33, y will be equal to this. When x is negative 1.33, y equal negative 1.33 cubed plus 2 by negative 1.33 squared minus 1. So y would be what? Now, I would have to use my calculator here. So, this is my calculator. Negative 1 is the same as 1.33 squared. So, plus open bracket, 2 times negative. No, let's not do that. Negative 1.33 square. Oh, negative 1.33 cube is going to be a negative. So negative 1.33 cube equal that. Good. Plus, open bracket, 2 times negative 1.33 squared. This squared should have been outside the bracket, you know. Right? But anyway, negative 1.33 squared is going to be the same as 1.33 squared. It will become positive anyway, equal that, minus 1. So y would be 0.7, call it 0.769, 0.769. So one of the stationary point is at negative 1.33, 0.769. The other one, when x is 0, when x is 0, y is what? Y is x cubed plus 2x squared minus 1. You know that y is x cubed plus 2x squared minus 1. So y would be 0 cubed plus 2 times 0 squared minus 1, which is just minus 1. So the other point will be located at 0 and negative 1. So negative 1.33, 0.769. So you're at negative 1.33 right here and 0.769. Good. And the other one is 0 and negative 1. You can see it on the curve. So those would be the locations of the stationary point. One of them is at negative 1.33, 0.769. That means if you project across, this is 0.769. Just like how this is negative 1.33. The other one is 0 and negative 1. Alright? Alright, so that's it for now. I'm going to want to let us look at a few more functions when you're required to find the locations of the stationary point. And then later on we can find the nature of the stationary point. I'll see you then.